İkinci Eurasia konferansına, Cogeneration konferansına panelimizle devam ediyor olacağız. Bu panelde de yine enerji dönüşümündeki enerji arz güvenliği ile ilgili yine Cogeneration tarafındaki yurt dışından da katılımcılarla beraber bir oturum gerçekleştiriyor olacağız. Panelin ana moderatörü olarak da Enerji ve Tabii Kaynaklar Bakanlığı'nda Genel Müdür Yardımcısı olarak görev yapan Sayın Engin İlseven yer alıyor olacak.
Öncelikle hepinizi şahsım ve bakanlığımız adına saygıyla selamlıyorum. Türkiye Cogeneration Derneği'nin düzenlemiş olduğu 2. Avrasya Cogeneration Konferansı'nın ilk paneline hepiniz hoş geldiniz. İlk panel olması sebebiyle ve aramızda yeni katılanlar olabileceği için tekrar etmek istiyorum. Konferansta simultane çeviri bulunmaktadır. Konuşmaları hangi dilde dinlemek isterseniz o dil butonuna tıklayarak konuşmaları takip edebilirsiniz. Ladies and gentlemen, good morning and greetings to all. Welcome to second Eurasia Cogeneration Conference, organized by Cogen Türk Association. I just want to remind that there is simultaneous translation in this conference. You can follow the speeches by just clicking on the language that you wish to select from the language button. Müsaadelerinizle konferansın enerji dönüşümünde arz güvenliği konulu ilk oturumunu başlatıyorum. İlk olarak bu konferansa katılmaktan mutluluk duyduğumu belirtmek ve davetleri için Türkiye Cogeneration Derneği'nin değerli temsilcilerine teşekkür etmek isterim. Malumlarınız olduğu ve önceki oturumlarda da belirtildiği üzere dünya olağanüstü bir dönemden geçiyor ve bu dönemde enerji sektörü gündemin en üst sıralarında yer alıyor. İklim değişikliğine yönelik endişelerin arttığı ve ülkelerin orta uzun dönemli hedefler açıkladığı günümüzde temiz enerji kaynaklarının bununla birlikte verimli, sürdürülebilir, adil bir kalkınmayı sağlayacak enerji dönüşümünün dünya genelinde ön planda olması gerekiyor. 2020 yılında hayatlarımız pandemiyle birlikte değişirken önce ekonomilerdeki ve enerji talebindeki daralmayı, sonrasında ise pandeminin etkilerinin azalmasının ardından ekonomilerdeki ve enerji talebindeki hızlı toparlanmayı yaşadık. Bu durumun arz kaynaklı gelişmeler, tedarik sorunları ile birlikte genel enerji arz talep dengesi üzerinde oluşturduğu olumsuzluğun etkisiyle 2021 yılının ikinci yarısında enerji fiyatlarında hızlı yükselişlere şahit olduk. 2022 yılının ilk çeyreğinde ise Rusya-Ukrayna savaşı sonrası doğalgaz, kömür ve ikincil bir ürün olan elektrik enerjisi için piyasalarda rekor düzeydeki fiyatlara tanıklık ettik ve hala etmekteyiz. İçinde bulunduğumuz dönemde özellikle enerji ithalatçısı ülkeler için enerji temin maliyetlerinin ülke ekonomik büyüklükleri içindeki payının kritik düzeylere yükselmesi ve bu durumun sürdürülebilirliğinin tartışılmasının yanı sıra enerji fiyatından bağımsız olarak varlığının da konuşulduğu bir ortam oluşmuş durumda. Bu bağlamda enerji dönüşümünde arz güvenliğini konuşacağımız bu panelde bugün ve gelecekteki enerji politikaları ve teknolojileri üzerinde duruyor olacağız. Bu oturumda 4 panelistimiz bizlerle birlikte olacak. İlk olarak Cogen Europe'un politika başkanı Alexandra Tudoroiu'dan Avrupa'daki enerji gündemini ve geleceğe yönelik yol haritasını dinliyor olacağız. Ardından Cockerill firmasından kıdemli satış danışmanı Eric Dabe'den hidrojen teknolojileri ve bu teknolojilerin gelecekteki rolüne ilişkin sunumunu alıyor olacağız. Sonrasında Amerika Birleşik Devletleri Nükleer Enerji Enstitüsü'nden kıdemli yönetici Marcus Nichol'den nükleer enerjideki gelişmeleri ve modüler nükleer reaktörler konusunda değerlendirmelerini dinleyeceğiz. Son olarak Enerji ve Tabii Kaynaklar Bakanlığı'ndan Daire Başkanı Özgür Sarhan'dan Türkiye'de enerji arzı ve güvenliğine yönelik genel görünümü ve değerlendirmelerini aktarmalarını isteyeceğiz. Tüm konuşmacılarımıza yeterli miktarda süre sağlanabilmesi adına kendilerine yaklaşık olarak 12 dakika süre ayrıldığını hatırlatmak isterim. Sayın Alexandra Tudoroiu, hoş geldiniz. Sözü size bırakıyoruz. Buyurunuz.
Good morning and thank you for the invitation to speak. I will share a few slides if that is possible. Okay, so I believe that you can see my slides now. Again, good morning to everyone. So I was asked today to speak about cogeneration in Europe, as well as the contribution of cogeneration that cogeneration can have towards security of supply, also given the quite dramatic context that we have at the moment. Zooming a bit out and talking about Cogen Europe and our vision, we do believe and stand for or working towards a net zero emissions energy system that is decentralized, resilient, carbon neutral, where cogeneration can contribute both now and by 2050. Our mission as Cogen Europe is to actually bring EU institutions and stakeholders together and shape better policies for higher energy efficiency, where again, cogeneration can play a role. We are the cross-sectoral voice of the cogeneration industry, and we represent, among others, Cogen Turk, but also other national associations, as well as corporate members that span from manufacturers to utilities to industrial users of cogeneration. And when it comes to manufacturers, we go from the kilowatt to the megawatt with micro CHP, but also CHP systems that have applications in district heating as well as industrial applications. So giving an overview of what is happening in the EU when it comes to the climate and energy policy landscape, as the introductory statement made clear, we are now in almost an emergency context when it comes to the energy crisis. However, we must not lose sight of the energy and climate objectives that the EU and also most European countries have set for themselves. So in the EU, we have the so-called EU Green Deal that aims at accelerating emission reductions, and that is achieved through the Fit for 55 package that is currently being discussed at European level. And there we're talking about very ambitious objectives in terms of energy efficiency, renewable energy, but also emission reductions. This is complemented by green financing. Of course, we are coming out of the of several lockdowns with the COVID pandemic, and for that, the European Union has set a recovery and resilience package, which has green criteria, and member states are to invest quite a lot of this funding in energy efficient and renewable projects. We also have the taxonomy regulation, which is also supposed to classify green investments. And there we see that cogeneration is well positioned. And then, of course, we have the energy price crisis, which originates back in 2021 with the economy picking up after the lockdowns. But now this is aggravated by the war in Ukraine. And then the EU has had quite a strong response in aiming to reduce dependency on Russian gas imports, to diversify gas supply from other sources, and also it has taken measures, and it's discussing measures on how to reduce demand and tackle potential supply gaps this winter. Some cross-cutting themes that we observe here. We have energy efficiency first. However, it has an end user focus, as we'll discuss later. So there's more of a focus on reduction in demand rather than improvement of energy efficiency when it comes to the various EU policies. There's a very much discussion over the phase out of fossil fuels and also the transitional role of natural gas, which in the current crisis is it has become a big point of debate. An increase in renewable energy shares and electrification is another strategy that is being pursued by the EU. And then for energy prices, there's definitely political interest and focus on protecting vulnerable consumers, but also protecting and maintaining industrial competitiveness, as the price crisis has affected quite a lot of industries in Europe. And then security of supply, of course. It's more the emergency situation where we see gas supply being at risk, but also more longer term with electrification and intermittent renewables putting pressure on electricity grids, and then resilience becoming an increasingly important element of the energy mix. Then what is our vision, and how do we talk about cogeneration in this context? Of course, we see a cogeneration as a key component or enabler of the future energy mix, but also an important solution that can support the energy system today, bringing energy efficiency, but also bringing resilience to the energy system. And we always try to focus on the energy system as a whole rather than silos. So rather than looking at the electricity system by itself, the gas sector by itself, and consumers all separately from each other, we see that energy systems are integrated, and this is how CHP can best contribute. And this is the same idea, zooming out. CHP has many different applications in industry, in district heating. More recently in micro CHP is being installed in homes, and it can really support with energy systems integration. So it can be optimized to support energy grids when there's no sun or no wind. And it's also key in terms of the hydrogen economy. Wherever valuable hydrogen is produced, it's important that that hydrogen, for instance, is used as efficiently as possible, be it in industry, but also in district heating and buildings. So the role of CHP and contribution towards the climate and energy objectives, both today and in the future. Today in Europe, we see that CHP produces 12% of electricity and 16% of heat. It empowers consumers. About 60 gigawatts is installed on key industrial sites, from the chemical sector to pulp and paper, alumina, ceramics, primary food processors. So really key industries. It ensures 70% of district heating heat, and more than 100,000 micro CHP systems are installed in buildings. And with its energy efficiency, it contributes towards energy savings of about 30 to 40 BCM. That includes about 15 BCM of direct natural gas savings. So in the current crisis, we estimate that this is about 15% of what EU must do to reduce its dependence on Russian gas. And this is one of the EU objectives. And also CHP is increasingly renewable. So at the moment, 30% of CHP is renewable, but that is growing, and the highest potential we think is, of course, bioenergy, but more significantly biomethane and hydrogen. And then finally, CHP contributes towards energy resiliency. It is a flexible source of electricity, and it's dispatchable. So increasingly what is happening, we see projects that where CHP can very rapidly ramp up and down to meet as in response to price signals and also to meet residual demand. And we see the contribution of CHP remaining important towards 2050. We've carried out a study which we can share with the participants as part of the slides. We've carried out a study on the role of CHP in 2030, and we see that making CHP part of the energy mix in Europe will bring cost reductions or overall cost reductions of 4 to 8 billion euro. These are net cost reductions, so it takes into account the investments that will need to be made into CHP capacity. And this is mainly due to energy savings, which will be even more important in the future than they are now. And in that context, we estimate that CHP will be delivering up to 16% of electricity and about 25% of heat, which is quite an important contribution still. And we also see that CHP can bring direct cost savings for users themselves. And here we have an overview of different CHP applications: district heating, industry, hospitals, for instance, where adding CHP to the heat mix of that site can actually bring significant cost reductions. This is again in a 2050 energy net zero energy system. We expect that energy prices will be still quite high despite very high shares of renewables, and in that context we think that CHP can also help. And this is a rather complex chart which comes from the Fraunhofer Institute, but it basically shows the residual demand. So the difference between demand and the supply of PV and wind, of intermittent renewables. So what is on top of the zero axis is actually demand that cannot be met with renewables, and that, I mean, this what is on top is going down, of course, as PV and wind deployment is increasing. But what we see is that the peak demand will remain important in the decades to come. And actually CHP can contribute significantly towards meeting those peak demands that will be quite expensive to deliver otherwise. So it's the most efficient source of backup for the energy system. But what we see also now with electrification is, of course, that CHP can very neatly complement electrification, because it produces electricity at the same time that heat pumps or electric vehicles will require that additional electricity to be produced. And with CHP, that electricity is more less carbon intensive and more efficiently to produce than with power only generation. And this,
Tudoroiu, can you
yes,
conclude in a couple of minutes?
I have this slide which shows the same picture, and then our final message is actually that we want an ambitious energy regulatory framework. We want ambition in energy efficiency, renewable energy, and we want cogeneration to be part of that picture. So thank you very much, and I'm happy to take any questions. Thank you.
Mr. Tudoroiu, thank you for your presentation. Mr. Tudoroiu mentioned briefly the overview of EU energy and climate policy landscape, as well as she stressed the importance of flexibility and resilience, especially as RES integration increases. Then she focused on cogeneration and the solutions that cogeneration power plants provide to the system. Then she also mentioned about the contribution of CHP in long term, especially its benefits in terms of cost reduction, energy savings, carbon dioxide emission reduction, and lastly, the coverage of peak demand, which will be the utmost importance in the future, especially as we rely more on intermittent renewables. Our next speaker is Mr. Eric Dabe. He will present hydrogen technologies and the role of hydrogen technologies in the future. Mr. Dabe, we leave the floor to you.
Thank you. So thank you for the introduction, and good morning, ladies and gentlemen. Let me start by a brief introduction of Cockerill Group. So Cockerill is basically a Belgian company, a pioneer in industry established over 200 years ago. So we have an international activity. You will find us in more than 50 countries. In terms of revenue, we are talking of 1 billion euro a year. So the organization counts today more than 5,000 people, and we have secured the growth of the group through organic growth, but also through acquisitions. So Cockerill is still privately held today. Our main shareholder is Mr. Bernard Sarhan, a French investor. And we have basically 6 areas of expertise today. I will not go into detail in those areas, but we have activities in renewables, energy solutions, environment, industry, defense, and services. Here are some figures about Cockerill hydrogen activities back in 2021. So our company delivered over 150 megawatt of water electrolysis. This basically represents over 33% market share last year. So we are truly the world leading player in this field. Our hydrogen organization counts today more than 250 people, and this is obviously steadily increasing these days. We have more than 30 years experience in the field of hydrogen solutions, and our core product, it's an alkaline electrolyzer, which is a 5 megawatt unit, generating 1,000 cubic meter per hour at 30 bar. We do enjoy quite a lot of references worldwide, about 1,000 projects. Our manufacturing capabilities annually are today close to 1 gigawatt, and we target 8 gigawatt by 2025. We have also last year decided to penetrate the mobility markets, and we are now developing our first hydrogen filling station. We have seen that our portfolio of electrolyzer is especially well suited to address the market of large-scale hydrogen production. And this is illustrated here in those 2 recent projects, the Nichol Baofeng Energy Group project, 110 megawatt hydrogen production plant by water electrolysis that was commissioned early this year in China. The use of hydrogen aims to replace and substitute coal, which is used in the chemical sector. In June, we were awarded an all-time high contract in our hydrogen division, the Sinopec project. Sinopec is basically the second largest oil company in China, and they will set up a 120 megawatt Cockerill hydrogen production plant. In both projects, the hydrogen production plant is powered by solar energy. So we can say we are truly producing green energy. And of course, the benefit will be a significant carbon dioxide emissions cut, which is estimated at 500,000 tons a year. Why hydrogen in the energy transition? Let me start by sharing with you the overall carbon dioxide emission per sector in 2021. So that was estimated at 36 gigaton, and we do see that some sectors are definitely contributing more than others in this figure. Based on a recent Hydrogen Council report, it was identified more than 35 existing and new hydrogen applications. And if we combine all those applications together, this would account for 60% of global carbon dioxide emissions. So this demonstrates that hydrogen has really great potential when it comes to decarbonize our society and play a meaningful role in the energy transition. If we look a bit deeper at the worldwide hydrogen demand outlook per sector, we do see that the hydrogen field will increase quite significantly in the years to come. So it is expected that the hydrogen demand will increase by approximately over 250% from today to 2030. This is quite significant. Although hydrogen is widely used already in some sectors, like in the refining and industrial sectors, like for ammonia production, methanol, and some other chemical applications, hydrogen is mainly today produced from fossil fuels. So we do expect that in the next 10 years, gray and black hydrogen, meaning produced from fossil fuels, will be substituted by green hydrogen. We also see that new applications will pop up for hydrogen in the years to come. We are thinking about the transport, power generation, also in the ammonia production, but using it as a fuel in the maritime sector, for instance, production of synfuel, buildings, and grid injection. So we do see that hydrogen has really, I would say, a versatile role in many applications. It was mentioned earlier today, but it is clear that the current energy crisis and the geopolitical risk linked to fossil fuel supplies are also good drivers to contribute to accelerate the deployment of this hydrogen economy. Looking at today's hydrogen feedstock, we will see, as I mentioned earlier today, that the hydrogen production is clearly dominated today by fossil fuels. This is amounted by over 96% of the overall hydrogen production. So water electrolysis is basically accounting for only less than 1% to date. On the right side, we basically compare the carbon dioxide emissions per, also I would say, feedstock. So first of all, talking about black hydrogen, which is basically produced from coal by gasification, we see that the carbon footprint is extremely high. It is estimated at, as an average, 20 kilo carbon dioxide per kilo hydrogen generated. Gray hydrogen, which is basically produced from natural gas by steam methane reformer, has a carbon footprint of roughly 10 kilo per carbon dioxide per kilo hydrogen, sorry. So an improvement versus black hydrogen, but still a very large footprint. And what we do see coming in the years to come is blue hydrogen and green hydrogen. Blue hydrogen is basically somehow gray hydrogen, where you do associate carbon capture storage. So this will be a significant improvement in carbon footprint. So that would be in the range of 2 up to 4 kilo CO2 per kilo hydrogen generated. But ultimately, we see the benefit of moving to green hydrogen production. The carbon footprint is close to 0. Green hydrogen is obviously producing hydrogen by water electrolysis from a renewable energy source. So green hydrogen is obviously very attractive, and everyone sees a great potential in this new methods of production. If we look at the competitiveness of hydrogen today, we do see that compared to blue and gray hydrogen, green hydrogen is obviously little competitive. But hopefully we do see a positive trend in the years to come, and it is expected that by 2030, green hydrogen will start competing with blue and gray hydrogen. And this trend will continue in the years to come, and this trend will basically only strengthen. If we look at 2050, we do expect that green hydrogen will be at an LCH level of 1 up to $2 per kilo and will outcompete gray and blue hydrogen. This trend will be obviously driven by different parameters. The carbon dioxide taxation is expected to increase gradually over the years. Countries obviously aim to reduce their reliance on fossil fuels and diversify the energy mix. This will be a strong contributor to deploy the renewable energy mix, and of course having access to cheap electricity, which is the main cost when you produce green hydrogen. We also do expect that the capex related to the technology will go strongly down. This will be driven by growing demand, lean manufacturing, framework agreement, etc. Technology improvement are also expected in terms of efficiency, size of the electrolyzer, current density, and even pressure. In this slide, you can see the roadmap on a worldwide basis in different regions. It is already announced quite many projects in the hydrogen field. Those are estimated today by 2030 at 300 plus gigawatt of low carbon hydrogen project. This is not only green hydrogen project, but we do expect that a large share of those projects will be allocated to green hydrogen production. Some regions are obviously in the lead, Europe with 80 gigawatt, and some of you may have heard that yesterday was basically a historical day in Europe, since Europe approved over 5 billion public funding to support hydrogen projects. China also has a strong initiative when it comes to hydrogen. They target 80 gigawatt by 2030, but all the regions are just behind. I'm thinking about Northern America, Australia, Southern America, and even Middle East. So what you do see here also, John Cockerill logo, those are the locations where we are currently building our manufacturing capabilities. So today we have close to 1 gigawatt in China. We are currently building a factory in Europe, in France, 1 gigawatt, and probably a second factory in Belgium too, and also in India, where we target 2 gigawatt in the years to come. And with this, I thank you for your attention.
Thank you, Mr. Dabe, for your excellent presentation. Mr. Dabe first mentions his company's recent and ongoing projects. Then he mentioned about where hydrogen is placed as of today and stress its importance in decarbonization. And he also underlines the expectation of huge increase in hydrogen demand in the years to come. And an important point, as of today, 96% of hydrogen is produced from fossil fuels. That's an important point. And then within this context, he mentioned about the cost of hydrogen production and the potential of cost reduction for green hydrogen and how this can be achieved. The motivations are presented by Mr. Eric Dabe. And lastly, you mentioned about the ambitious targets around the world in terms of hydrogen production and electrolyzer installations. We would like to thank you for your presentation. And next, we will have Marcus Nichol from USA Nuclear Energy Institute. He will present us the developments about nuclear energy and specifically modular nuclear reactors. The stage is yours, Mr. Nichol.
Thank you very much, and good morning. So the Nuclear Energy Institute is the organization in the United States that represents the nuclear industry. And so I appreciate the opportunity to talk to you all today about the developments of advanced nuclear in relation to cogeneration. I want to begin with why so many people, and not just in the United States, but around the world, are starting to look more seriously at advanced reactors. And this is specifically for the electric grid, but it has similar conclusions for cogeneration applications. And that is, what we find is that the lowest cost electric system is one that has nuclear as part of the generation portfolio. This results was from a study that looked at how do you get to reduce the carbon by 95% in the United States for the electric grid. And they found, they ran two scenarios. The first is, well, what if advanced nuclear comes in at the costs that we're expecting them to? And they found that nuclear would be then 43% of the generation in the United States. Today, it's about 20%. And that would be an additional 300 gigawatts of new nuclear. Today in the United States, we're at 90 gigawatts. So it's four times more than we are today. Wind and solar would still be a big contributor at 50%. And then the other scenario, they said, well, what if there are constraints on advanced reactor deployments, whether the regulator is too slow, or whether we have supply chain disruptions for critical minerals, as an example? What would be the impact? We found that there would still be a need for 60 gigawatts, so it's still a lot of new nuclear, but not as much. Nuclear would then only be 13% of the grid. Wind and solar would be 77%. But the most important thing is they looked at the cost between the two systems, and they found that the one that had the smaller amount of nuclear would increase the cost to the customers by a total of $450 billion. And so this just underscores the importance that if you want clean and reliable and affordable, then nuclear really needs to be a part of the generation mix. So in the United States, we have over 90 plants in operation today, or 90 reactors in operation today at a number of plants in a number of states. So this is just to show you the scale of nuclear in the United States today. For advanced reactor development, we have a portfolio of products that are being developed to meet a diverse set of market and customer needs. And we can categorize them by two parameters. One is size. And so on the left are the very smallest reactors. We call them micro reactors. They're less than 20 megawatts. They could be a little bit bigger, a little bit smaller. Some are as low as 1 megawatt. And these are really well positioned for remote markets. I'll have a little bit more information on those in a little bit. Most of the rest fall in the small category, which is less than 300 megawatts for a reactor. They're modular, so you can put more than one reactor together. And so you can have a plant that is quite large. So for example, NuScale is a 77 megawatt reactor, but if you put 12 of them together, then the plant is over 900 megawatts. So you can get large plants out of small reactors by putting several of them together. The other parameter that we divide them by is the coolant type. This is the material that goes through the core to keep it cool and provides the energy transfer, the heat transfer to the balance of plant, whether you want electricity or steam or another form of heat. And we have water, which is what is used in the United States today for our reactors and most reactors in the world. And then there's three non-water cooled technologies. There's high temperature gas, which is primarily helium. We have liquid metal, which could be lead or sodium. And then we have molten salt. It's essentially like table salt, but at a very high temperature, it becomes liquid and a good heat transfer medium. And the great thing about the non-water cooled is that they can reach much higher temperatures than water cooled. Now, water cooled can reach temperatures that's useful in cogeneration for some applications. The non-water cooled brings that heat up to higher temperatures that's useful for other applications. I have more information on that. So this is a video, if it works.
Every country needs energy. Some need electricity. Others require hydrogen. Others need process heat. But every sector is looking to decarbonize, and they're looking to advance nuclear. It provides any output required in any combination required. Advanced nuclear is affordable, and advanced nuclear is reliable, clean, firm power that partners with wind and solar. It works at every scale to power any community, driving economic growth, offering a diverse range of technological solutions to meet the diverse range of needs. Among NEI members alone, over 300 reactors are already envisioned, and we're just getting started.
All right, so that was a video. I'll go through some more detail on that. The video mentioned we're developing a range of sizes. I also talked about that, and a variety of outputs. So we can do electricity, we can generate hydrogen, and you'll see in a minute that we can generate hydrogen not just through electrolysis, but we can use heat assisted or even very high temperature generation of hydrogen to do it more efficiently. And we can use process heat directly for a multitude of uses. And I'll go into a couple of those in the next slide. I'm coming back to microreactors and the markets that are opportunities for them. So these are areas that otherwise could not utilize nuclear energy for both electricity and for heat. And we have two types of microreactors. We have a stationary. Those are intended to stay there for a very long time, 10, 20, 40 years. This would be remote villages. It could be in the Arctic. In the United States, we're looking at Canada, but Alaska, and Canada is also looking at them. It could also be islands, anywhere that you're far from the grid. Microgrids, this could be to power emergency facilities like hospitals. It could also be at the end of the line, so grids that have a long line and points that are far from the generation are very vulnerable to disruptions. And so you could put a microreactor at the end of the line as a sort of anchor to help provide resilience. Mining and industrial, and then also defense installations. And we have mobile uses as well. Mobile would be something that operates for a period of time. It could be a couple of months, and then it would move to another location and you would operate it there. And their applications would be humanitarian and disaster relief. And then also our military is looking at it for ground operations. This is the picture of different process heat applications and their temperatures. And we're going to look at what nuclear can do to meet those temperature and heat demands. So the first are water-cooled reactors, and this shows that they can go up to more than 260 degrees Celsius. So you're great for district heating, desalination, paper and pulp, even some tar sands operations. The next are metal-cooled reactors, which reach temperatures 540 C and higher. And now we're getting into things like oil refining and some methane refining, hydrogen production. We get into salt-cooled reactors, and now we're getting into high-temperature steam electrolysis for hydrogen production, some petrochemical applications, and then finally gas-cooled, which have the highest temperatures up to 800 C, can do even more than that, even hydrogen production at thermochemical ranges. And so it just shows you that different technologies are useful for different heat applications. This slide talks about nuclear for district heating specifically. And I bring this up because all of the advanced reactors can provide district heating, but also because many people don't know that nuclear today provides district heating. Not so much in the United States, but other countries, they provide district heating, especially in Northern Europe. And so we actually have 43 reactors around the world that provide combined heat and power for district energy. That's 10% of the power reactors in operation. And that hot water can be economically delivered up to 100 kilometers away. And so we have a great range with this district heating. And this is just a schematic of how it would work. And so there are reports with more information. IAEA has a report on different uses as well. A lot of people are looking at nuclear to replace coal plants. And one of the reasons is because they utilize the same footprint. So you could use the exact same site. You'd have to replace many of the heat generation buildings. There's a question on whether you could use the turbine generator. Probably you would want to replace that, but there are possibilities to reuse it. Certainly you could reuse the transmission system and the transformers, and that is very valuable. And but it's about the same footprint in terms of power output. The interesting thing is that it's also about the same number of jobs, and we find that many of the coal workers can be retrained with not much effort to become nuclear power plant workers. And when you look at it, nuclear offers some of the highest wages of any generation technology. And so you get carbon-free, grid-firm electricity, and you get the benefits located in the community. And so it's a good like-for-like replacement of a coal plant. In the United States and Canada, we're looking currently at 20 projects that are being planned or considered for new advanced reactors between now and about 2030. When we look globally, that expands to greater than 30. Most of those globally today are in Europe, Eastern Europe, and that interest is continuing to grow domestically and internationally. The states are as well providing policies to incentivize nuclear. Our federal government has been doing that for a long time. We just passed a bill last month called the Inflation Reduction Act, which provides a lot of energy policy to help spur advanced reactor deployment. Finally, I want to talk about the system benefits of advanced reactors. Sometimes we call them SMRs when we're focused on grid scale small reactors. And this is a list. There's long-term price stability because they're low fuel and operating cost. It's high capital cost, but the operating costs are low. The price stability is for the very far future is there. And so in the United States, even we look at projects that were over cost back in the 1970s, and people were worried about them because they were over cost. But today, there's some of the lowest cost power producers in the United States. So it just goes to show how valuable that long-term price stability is. Reliable dispatch, 24/7, 365 days a year operation, high capacity factors. They only refuel once every 18 to 24 months currently. Some of the advanced reactors are looking at 10 to 20 years. We're building in flexibility to integrate with renewables and storage. We can even pair these with heat storage, which is even more efficient than battery storage. Great land utilization for the efficient use of transmission, but also if land is scarce. So you can get a terawatt hour of electricity out of 0.1 acres, where wind and solar would take up more land. Environmentally friendly, we all know there's zero carbon emissions, but what many don't know is that nuclear is one of the lowest total carbon footprints. It's on par with wind which is even below solar. So when we talk about the green hydrogen, which is primarily referring to renewables, it's the same level of carbon dioxide associated with it for nuclear plants. So we fit within green, although not technically, certainly philosophically. And we have black start capabilities, so these can operate independent of the grid. Because of the safety features built into these, they don't have to rely on offsite power for safety, so they can power through storms and other events, and then they can be the anchor of the grid to help it get started up after the disaster. I did actually have a couple other slides. One is if you are thinking about a nuclear program or deploying additional reactors, recognize that it is a long-term relationship, and so who you do business with is very, very important. There are many countries out there to do business with. Certainly, China and Russia are building the most reactors in the world today, but the United States, we view ourselves as one of the most stable and sound partners on advanced reactors deployment. And so that relationship goes from licensing, construction, operations, decommissioning, and so we can offer products and services in all of those areas. And with that, happy to take any questions at the right time.
Thank you very much, Mr. Nichol, for your informative presentation. Mr. Nichol underlines a couple of vital points, the first of which is that he compares the lowest cost system with a moderate share of nuclear energy and an energy system with nuclear energy constraint, and he underlined that nuclear energy is necessary if we want to be both clean and affordable as well as reliable. And also he mentioned two critical parameters of advanced nuclear technologies, the first of which is size and the last is the coolant type. Then he mentioned about the uses of advanced nuclear technologies, and he mentioned an important point that hydrogen can be produced through heat processes aside from electrolysis. And then he mentioned about the deployment plans in US and several benefits of small modular reactors. The first of which is price stability, and this is arguably the one that the world badly needs as of now. Thank you very much for your presentation, Mr. Nichol. Now we have the last speaker, Mr. Özgür Sarhan from Ministry of Energy Resources. He will talk about energy supply and security, and within this context, the general overview. The stage is yours, Mr. Sarhan. Mr. Sarhan, we cannot hear you.
Now, can you hear me?
Yes, we can hear you.
Okay. Şimdiye kadar kıymetli sunumlar dinledik. Umarım bu etkinlikte tüm katılımcılar açısından faydalı olur. Ben Özgür Sarhan, Enerji Bakanlığı'nda çalışıyorum. Enerji Arz Güvenliği ve Piyasalar İstatistik Dairesi Başkanıyım. Dairemiz temel olarak arz güvenliğinin izlenmesi ve özellikle uzun dönemli politikaların geliştirmesi hususlarında çalışmakta. Bugün de kısaca ülkemizin arz güvenliği planlamasına yönelik hususlarını arz edeceğim. Temelde aslında bizim mevcutta yer alan kanunlarımızı incelediğinizde elektrik piyasası kanunu, doğalgaz piyasası kanunu, petrol piyasası kanunu aslında hepsinin temelinde yeterli, kaliteli, kesintisiz, karşılanabilir, ödenebilir de diyebiliriz aslında ve çevreye duyarlı bir şekilde enerjinin tüketicilere arz edilmesi yer almakta ki bu tanımlar aslında hem Uluslararası Enerji Ajansı hem de Avrupa Birliği'nin enerji güvenliği, enerji arz güvenliği tanımlarıyla örtüşmekte. Biz de aslında politikalarımızı ve uygulamalarımızı bu şekilde gerçekleştirmeye çalışıyoruz. Peki arz güvenliğini nasıl izliyoruz, nasıl analiz ediyoruz? Bunun için aslında 4 aşamadan oluşan bir yöntemimiz var. İlk önce tabii ki izlemek. Bunun için de çeşitli raporlamalarımız var. Düzenli olarak hazırladığımız ve özellikle de bakanlık makamına arz ettiğimiz. Bu raporlamalar tabii ki saatlik bazdan tutun yıllık baza kadar analizleri içermekte ve raporlamaları yapmakta. Tabii ki özellikle zorlu dönemlerden önce, kış dönemlerinden önce ilgili kurumlarımızın da katıldığı analiz çalışmaları yapıyoruz. Stres testi uyguluyoruz hem iletim hem dağıtım seviyesinde ve gerçekleşebilecek sıkıntılara karşı da acil durum planlarımız mevcut. Risk analiz çalışmalarımız var, modelleme çalışmalarımız var, kendimizin geliştirdiği, in-house geliştirdiğimiz modelleme çalışmalarımız var. Bu çalışmalar sonucunda da özellikle kısa ve orta dönemde bir risk varsa bunu çeşitli raporlarla paylaşıyoruz. Tabii ki önleyici yaklaşımlarımız da var. Kritik enerji altyapı güvenliği bu noktada önemli. Kriz yönetimi de önemli ve tabii ki son dönemde, son 10 yılda diyelim özellikle de bilgi güvenliği, siber güvenlik alanında da çeşitli çalışmalarımız oldu. Son dönemde özellikle literatürde ve uluslararası kuruluşların gündeminde de olan bir konu var. Enerji System Resilience diyoruz. Enerji sisteminin dayanıklılığı, dirençliliği olarak da çevirebiliriz. Ajansa göre de bu enerji sistemin dayanıklılığı özellikle şok anında, yani herhangi bir beklenmeyen durum anında, ki bu son dönemde gerçekleşmiş COVID-19 salgını olabilir. Rusya-Ukrayna krizini sayabilirsiniz. Özellikle yenilenebilir tedariğini etkileyebilecek noktaya gelmiş çip krizini sayabilirsiniz. Avrupa'yı bugünlerde etkileyen nükleer kısıntıyı sayabilirsiniz ve son dönemde Rusya-Ukrayna savaşından sonra Avrupa'da yaşanan doğalgaz sıkıntısında bunu ekleyebilirsiniz. Aslında enerji sistemlerinin de bu şoklara karşı dayanıklı hale getirilmesi gerekiyor. Planlamanın da direnci arttıracak şekilde yapılması gerekiyor. Biz de çalışmalarımızda bunlara dikkat ediyoruz. Birçok baktığımız gösterge var. Literatürde de yer alıyor bunlar. İşte en basitinden doğalgazda giriş kapasitesi, giriş noktası sayısı, doğalgaz ithalat bağımlılığı ya da ithalat bağımlı, enerji ithalat bağımlı, enerji fiyatlarındaki stabilite ve özellikle birincil enerji kaynaklarında çeşitliliğin artırılması. Bizde özellikle 2017'de Milli Enerji ve Maden Politikası'nın açıklanmasından sonra enerji kaynaklarının çeşitliliğinin artırılması noktasında birçok adım atıldı. Sayın Bakanımız da bahsetmişti. Örneğin Sakarya sahasının keşfi, yeni doğalgaz ve hidrokarbon saha arama çalışmalarının başlatılması, bununla birlikte doğalgaz tarafında yapılan altyapı geliştirmeleri bunların birer örneği. Çeşitli endeksler var takip ettiğimiz. En basitinden Herfindahl-Hirschman Index buna örnek verilebilir. Ülkemizde elektrik üretiminde örneğin en çeşitli kaynağa sahip ülkelerden birisi. Özellikle büyük ülkelere baktığımızda. Bunu tabii ki başarırken de son dönemde, yani uzun vadede ülkemizin talep artışına baktığımızda önemli başarı olarak görüyoruz. Birincil enerjide yaklaşık %3.3'lük bir uzun dönemli ortalamamız var ki bu birçok Avrupa ülkesinin de çok üzerinde. Sadece Çin ve Çin'in gerisinde olduğumuzu görüyoruz. Elektrik tarifine baktığımızda da sağ tarafta yine aynı şekilde 4.4'lük bir uzun dönemli ortalamamız var. Yine birçok Avrupa ülkesinin ve OECD ülkesinin ortalamasının üzerinde olduğunu görüyoruz ki talebin de artmaya devam ettiğini göz önüne alırsak daha enerji sektöründeki yatırımların da devam etmesi gerektiğini düşünüyoruz. Elektrik tarafında kurulu gücümüz 100.000'i aşmış durumda. 102.043 megawatt Ağustos sonu itibariyle, ki yenilenebilir kaynaklar bunun yaklaşık %55'ini oluşturuyor. Özellikle 2010 yılından sonraki dönemdeki yenilenebilir kapasitenin gelişimine baktığımızda ciddi bir artış olduğunu görüyoruz. 20 binlerden neredeyse 60 bin megawattlara gelmiş durumdayız. Son dönemdeki artış da rüzgar ve güneş kaynaklı olduğunu görüyoruz. Tabii ki kurulu gücün gelişimi güzel ama kurulu güç üretim kapasitesi anlamına gelmiyor. Ne demek istediğimi anlatayım. Kurulu güçten aslında %100 anlamda sürekli olarak faydalanamıyoruz. Bakımda olabilen santraller var, arızalı olanlar var, yaşlanıp verim kaybına uğrayan santraller var. Örneğin 2021'de çok sıcak geçmişti yaz dönemi. Bazı santrallerin, özellikle doğalgaz santralinin ısı kaynaklı yine verim kaybına uğradığını görebiliyoruz. Şebeke kısıtlarımız olabiliyor, kaynak yetersizliği olabiliyor ki örneğin 2020 ve 21 kurak bir dönemde, şurada bahsedeyim, kurak dönem olduğu için de hidrolik kapasitemizden yeterli ölçüde yararlanamadık. Ortalamada 83 milyarlık bir üretim yapabilirken 2021'deki üretimimiz 56 milyar kilowatt saate kadar düştü. Bu aslında 27 milyar kilowatt saatin başka kaynaklardan karşılanması gerektiği anlamına geliyor. Tabii ki burada Cogen santrallerinin de kendi kendine yetebilirliğini göz önünde aldığımızda bu dönemde bize ciddi katkı verdiğini gördük. İlerleyen dönemde de yine benzer durumlarda katkı alabileceğimizi düşünüyoruz. Tabii ki rüzgar ve güneş kapasitesinin artması bize yeni bir problemle karşı karşıya getiriyor. Kesintili, intermittency dediğimiz kesintili üretim. Zaman zaman rüzgar ve güneşten tam kapasiteye yakın faydalanabiliyoruz ama zaman zaman da neredeyse %0'lara düşen bir kapasite faktörü var. Şu anda ikisinin kurulu gücü toplamı yaklaşık 19 bin megawatt. Aslında bizim yönetmemiz gereken bir 19 bin megawatttan bahsediyoruz. Bu kurulu güç arttıkça da bu marjın artacağını öngörebiliriz. Bizim birazdan bahsedeceğim planlama çalışmalarımızda da çok ciddi kurulu güç artışı bekliyoruz rüzgar ve güneşte. Yönetilmesi açısından da ekstra önlemler alınması gerektiğini düşünüyoruz. Talebi geçmişte artmıştı. İlerleyen dönemde de yine artmaya devam etmesini bekliyoruz. En son yayınladığımız talep projeksiyonunda 2040'da 590 terawatt saate ulaşmayı bekliyoruz. Peki son dönemde özellikle geçen senenin sonuna doğru Sayın Cumhurbaşkanı tarafından açıklanan ulusal 2053 net zero hedefi bize ne getirecek enerji sektöründe? Biz bunun için kanunun da bize verdiği görevle bir ulusal enerji planı hazırladık ve muhtemelen bir iki hafta içinde de yayınlamayı planlıyoruz. Arz tarafını ve talep tarafını ayrı ayrı çalıştık. Talep tarafında ekonomik gelişmeler, nüfus beklentileri, teknolojik dönüşüm, enerji verimliliği gibi konuları detaylı inceledik. Arz tarafında da yenilenebilir gelişmeler, nükleer gelişmeler, Cogen tarafındaki gelişmeler, kömür politikası, karbon emisyonları gibi yeni teknolojiler gibi birçok hususa baktık ve planı hazırladık. Plan 2053 yılındaki net zero hedefine ulaşacak enerji sektörü için de enerji sektörünün net zero hedefine ulaşacak bize bir yol haritasını çizmekte. Sonuçları da paylaşmış olacağız. Özellikle rüzgar ve güneş tarafında ciddi bir atılım bekliyoruz. Diğer kaynaklarda da net sıfıra ulaşacak şekilde bir dönüşüm olacak, olmalı. Tabii ki planlama yapmak özellikle bu konjonktürde, global konjonktürde biraz zor. Çünkü birçok belirsizlik var. Bu Dünya Enerji Konseyi'nin son yayınladığı rapordan belirsizliklerin de arttığını görmekteyiz. Yani emtia fiyatlarından tutun, jeopolitik, iklim değişikliği yönetiminden ekonomik büyümeye kadar birçok alanda belirsizliklerin genel olarak arttığını görmekteyiz. Bu da tabii ülkemizi doğrudan etkilemekte, bizim planlama çalışmalarımızda doğrudan etkilemekte ve bu belirsizliklere ilavede yeni değişimlerin planlamayı zorlaştırdığını görmekteyiz. Örneğin 1999 yılında Uluslararası Enerji Ajansı'nın yayınladığı Dünya Enerji Görünümü'nde 2020 için hidrolik kapasitenin 1078 megawatta, gigawata, diğer yenilenebilirlerin yani rüzgar, güneş, jeotermal ve biyokütlenin sadece 142 gigawata ulaşacağı öngörülmüş. 2009'a geldiğimizde aynı değerlerin hidrolikte yaklaşık olduğunu, rüzgarda 422 gigawata ve güneşte 102 gigawata ulaşacağını öngörmüş ajans. Ama 2020'deki gerçekleşmelere baktığımızda rüzgarda 730 gigawata, 10 sene önceki tahminin neredeyse 2 katı, güneşte 7 katı, 716 gigawattlık bir değere ulaştığımızı öngörüyoruz. Yani aslında biz 30-40 seneyi planlıyoruz ama 10 senelik dönem bile bu global konjonktürde çok farklı şekilde tezahür edebiliyor. Biz de bunu bir şekilde planlama çalışmalarımıza yansıtmaya çalışıyoruz. Sonuç olarak önümüzde 2053'e doğru uzun bir yol var. Tabii ki bir salgından çıktık. Devam eden bir savaş var. Net zero hedefleri var. Bununla birlikte gelişen birçok teknoloji var. Sonuç olarak enerji dönüşümü yaşamamız gerekiyor. Bunu tabii yaparken de şoklara karşı dirençli, cevap verebilen, rasyonel, esnek ve dijital bir dönüşüme aslında ulaşmamız gerekiyor. Tabii ki bu dönüşümlerin de global olarak bir politik istikrarın olduğu bir dönemde olması gerekiyor ki bu hedeflere ulaşabilelim. Kısacası zorlu bir yol bizi beklemekte. Teşekkür ediyorum dinlediğiniz için.
Özgür Bey'e sunumları için teşekkür ediyoruz. Özgür Bey de kısaca enerji arz güvenliği ve izleme süreçlerine ilişkin genel konsepti ortaya koyduktan sonra enerji sistemi dayanıklılığı kavramı ve takip edilen HHI endekslerinden bahsetmiş oldu. Kurulu güç ve üretim yeteneği gibi sıklıkla karıştırılan iki kavram hakkında bizi aydınlattı. Hidroelektrik üretim ve ülkemizdeki kesintili üretim davranışıyla ilgili önemli birkaç bilgi verdi. Belki de en önemlisi Türkiye Ulusal Enerji Planı'nın hazırlık çalışmaları sürecinde kullanılan girdilerden, planın yaklaşımından ve yakın zamanda planın yayımlanmasının planlandığından bahsetmiş oldu. Son olarak da dönüşümün temel unsurlarına yer vermiş oldular. Süremizi aştık sanırım. 1 saati aşmış olduk. Ben katılımcılara sabırları için teşekkür ediyorum. Bu oturumda konuşulan konuların, verilen bilgilerin, yapılan sunumların tüm katılımcılarımız için faydalı olmasını umuyorum. Panelistlerimiz adına herkese teşekkür ediyorum. Bu şekilde oturumu sonlandırıyoruz. Sözü Yavuz Bey'e ve Merve Hanım'a bırakıyorum.
Çok teşekkürler Engin Bey. Enerji dönüşümünde arz güvenliği oturumunda panelistlere ben de çok teşekkür ediyorum.